Constructing urban traffic tunnels with advanced TBM systems delivers precise excavation, continuous ground support, and safe underground transportation solutions beneath busy cities. The giant tunnel boring machine Jazla represents one of the most advanced pieces of underground construction technology deployed for the Riyadh Metro project. Officially launched in July 2015 by Prince Faisal bin Bandar, governor of Riyadh, Jazla was introduced as the primary machine assigned to excavate the Orange Line tunnel part of the extensive metro network being developed by the Riyadh New Mobility Consortium. With an impressive diameter of 10 meters and weighing approximately 700 tons, Jazla is engineered to operate in challenging urban geology while maintaining exceptional precision. The machine began its drive along a 5.8-kilometer underground alignment beneath downtown Riyadh, heading toward and eventually passing directly below the city's main train station. Its massive cutting head is designed to simultaneously excavate soil, support the surrounding ground, and install precast concrete lining segments, ensuring continuous progress and maximum safety in densely populated areas. Salini Imprezillo, serving as the leader of the A&M Consortium, is responsible for delivering the entire 41.2-kilometer Orange Line, the longest line of the Riyadh Metro. Jazla plays a crucial role in achieving this milestone, enabling rapid, mechanized tunneling with minimal surface disruption. As it advances meter by meter, the TBM demonstrates the scale, engineering capability, and ambition behind Riyadh's transformation into a modern, high-capacity urban transit hub. The construction of the Eppenberg tunnel progressed from complex surface works to the underground breakthrough of a more than 600-meter section excavated by a 100-meter-long tunnel boring machine. Before tunneling could begin, extensive open-cut works were required at the east portal, where a massive excavation pit was created on the steep slope of the Eppenberg. This area served as the assembly platform for the TBM. To stabilize more than 300 meters of hillside, engineers applied multiple slope support methods, while the heavily trafficked cantonal road had to be relocated several times. Within the constrained corridor between the temporary road and the existing rail line, serving Schonenwerd Station over 9 kilometers of drilled piles, and 24,000 square meters of sheet pile walls were installed to secure the pits. Some excavation walls reached heights of up to 26 meters, forming the foundation for the later tunnel structure. Because the completed tunnel must resist significant ground pressure from the steep slope, highly robust reinforced concrete linings were cast using mobile formwork carriages. From the front of the excavation pit, the conventional excavation of the starter tunnel began through loose ground unsuitable for the TBM. Using the pipe roof method, crews advanced in 10-meter stages until solid rock was reached, allowing installation of the machine. The cutter head was lifted into position in October 2016, and by January 2017, the TBM began advancing. Its 13-meter cutter head fragmented rock under high pressure, while conveyors removed muck and precast segmental rings were installed every 2 meters. With continuous propulsion, grouting, and ring building, the TBM steadily progressed toward the final breakthrough, The turnaround of the Alice tunnel boring machine inside the northern approach trench stands as one of the most complex engineering operations of the project. As Alice approached the northern portal, crews first installed a large temporary frame to support the head wall. Once the wall was safely removed, the TBM was transferred onto specially designed temporary steel and concrete cradles. These cradles not only carried her two 500-ton weight, but also enabled the controlled rotation and sliding of the machine across a lubricated steel floor toward the new tunnel alignment. Because the northern portal measures only about 42 times 42 meters, while Alice extends more than 90 meters, engineers had to dismantle the TBM into discrete components. Each section was maneuvered individually, supported by detailed planning, 3D modeling, clash detection, and precise temporary works design. For the first 250 meters of the new drive, half of the machine operated in one tunnel, while the remaining gantries remained in the adjacent tunnel, requiring temporary connections and an auxiliary backup gantry elevated 10 meters above ground. All operations took place 25 meters below surface, relying heavily on large cranes to move equipment in and out of the NADAT. A unique feature of the turnaround was the use of lanolin-based grease, derived from New Zealand sheep wool, to reduce friction beneath the cradle and assist the 180-degree rotation. Despite extremely tight clearances of just 150 millimeters, the turnaround was completed safely, ahead of schedule, and under budget. This achievement highlights exceptional teamwork, meticulous engineering, and the logistical mastery required to redirect such a massive TBM for the northbound tunnel drive. The Hydroshield tunneling method represents a highly sophisticated technology designed for constructing underground infrastructure beneath urban buildings, traffic corridors, and groundwater-bearing loose soils. Its key advantage lies in enabling settlement-free excavation, even with extremely small overburdens, allowing tunnels to pass safely under roads, tram lines, utilities, and waterways. The system uses a two-part TBM configuration, consisting of the shield with its geology-adapted cutter head, and a backup section housing all logistical installations. The cutter head is engineered to handle both loose materials and hard blocks, as well as reinforced concrete interfaces. Central to Hydroshield technology is face support using a Bentonite suspension. As excavation proceeds, the suspension forms a thin filter cake that stabilizes the face and prevents air loss, ensuring safe access to the excavation chamber for tool changes or obstacle removal. Pressure locks inside the shield allow workers to transition between atmospheric and hyperbaric environments, although the limited working time under high pressure demands excellent teamwork and expertise. As the machine advances, precast concrete segments are installed within the shield to support the newly excavated void. Bentonite mixed with spoil is continuously pumped to a separation plant where reusable fractions are recovered and the clean suspension is returned to the TBM. This closed-loop system ensures stability, precision, and safety throughout the entire excavation process. The southern tunnel of the Waterview Connection forms a key part of Auckland's western ring route, providing a seamless underground link between SH20 at Mount Roskill and SH16 at Point Chevalier. This 2.5 kilometers southbound tunnel was delivered under strict consent approvals, incorporating advanced construction methods to manage ground conditions and community impacts. After extensive mitigation works and related urban improvements, the tunnel opened in July 2017. Today, it carries 3 traffic lanes and significantly enhances network capacity and travel reliability across the region. Alice, the tunnel boring machine that excavated 2.4-kilometer tunnels for the Waterview Connection, was systematically dismantled after completing her mission. Over nearly 3 months, crews worked underground to take the TBM apart piece by piece, carefully extracting each section from the completed tunnel. Once above ground, the disassembly continued with strict procedures. Every component was thoroughly cleaned, greased, inspected, and formally signed off before being prepared for transport. Many sensitive parts were additionally wrapped in protective plastic to shield them from weather exposure. The largest elements, most notably the 270-ton main drive, were far too massive to be broken down further, and therefore had to be transported intact. Moving these oversized loads required heavy-duty transporters, configured with 2 prime movers pulling and 1 pushing. Each truck operated on 12 axles and 16 wheels, giving a total rolling system of 192 tires supporting the convoy. Because of their enormous size, transporting these components to the port of Auckland demanded extensive planning, scheduled road closures, and the temporary removal of street furniture along the route. To limit disruption, all movements were carried out at night, with the convoy traveling through suburban streets in central Auckland at speeds no greater than 15 kilometers per hour. After 3 years of service in New Zealand, Alice was finally shipped back to Germany, her work at Waterview successfully complete. The June 2016 time-lapse captures key construction works at the Southern Approach Trench, the Waterview Reserve Skate Park, and the Northern Ventilation Tunnel of the Waterview Connection, New Zealand's largest ever road project. It shows precast panel installation along the northbound lanes, active excavation to the underside of the capping beam, and prop beam works between the NAT and NVT pipe bridge, highlighting the project's scale and technical precision. Robbins designs and supplies advanced tunnel boring machines for hard rock and soft ground, including EPB, Slurry, single and double shield TBMs. Founded in 1952, the company offers complete solutions from TBMs to conveyors and segment erectors, providing global expertise, innovation, and field support for diverse tunnel projects. The Robbins Crossover XRE TBM, measuring 9.26 meters in diameter, is advancing the Ohio Canal Interceptor Tunnel in Akron. Designed for varying geology, the machine tackles soft ground, mixed ground, and hard rock as it progresses toward downtown, finishing near the stadium. Its cutter head efficiently handles both soil and rock, transitioning seamlessly between conditions. Muck is transported through a large screw conveyor to the tunnel conveyor, enabling continuous excavation. The initial 800-foot section posed significant challenges, but Robbins' technical staff ensured smooth operation and rapid adaptation. Upon breakthrough, the TBM is fully retrieved, and final connections, vent installation, and surface structures are completed. This robust machine ensures reliable stormwater management and clean water discharge into the Cuyahoga River. The construction of the MRT Malaysia SBK line marked a significant milestone in urban transit development, with a series of tunnel breakthroughs representing major achievements. The first breakthrough was completed on December 24, 2013, signaling the successful connection of the initial tunnel segments. This was followed shortly by the second breakthrough on January 9, 2014, demonstrating the steady progress of tunneling operations. Only a week later, on January 16, 2014, the third breakthrough was achieved, further advancing the underground alignment. After several months of continuous excavation, the fourth breakthrough occurred on April 8, 2014, highlighting the efficiency and coordination of the project teams. The pace continued in the later stages, with the seventh breakthrough recorded on October 16, 2014, followed by the eighth on October 21st and the ninth on October 29, 2014. Each of these breakthroughs reflected careful planning, precise engineering, and the use of advanced tunnel boring machines to navigate complex geological conditions. The final stages of tunneling culminated with the 10th breakthrough on January 3, 2015, immediately followed by the 11th on January 4, 2015. The 12th and last breakthrough was achieved on April 11, 2015, marking the completion of the main tunneling works. These milestones not only symbolized technical excellence, but also brought the project closer to providing a modern, efficient, and reliable mass transit solution for the people of Malaysia. The systematic sequence of breakthroughs showcased the dedication and skill of the entire construction team. The Evergreen Line Tunnel Boring Machine is a remarkable piece of engineering, shown here during testing and commissioning. Its cutter tools at the base loosen soil, which is collected in a chamber behind the TBM face and removed via a screw conveyor. Monitored from the control room, the material moves along a conveyor through the tunnel and emerges at the tunnel works yard, where a second conveyor deposits it beside Barnett Highway for transport to an approved disposal site. Meanwhile, prefabricated reinforced concrete tunnel liner rings are delivered inside the tunnel on a specialized mine service vehicle, which always moves forward. Ring segments are lifted and transported through the TBM backup system to the ring erector. Using a vacuum, the erector positions each segment while heavy-duty jacks secure them. The final key segment locks the ring, bolts seal it, and grout fills the gaps outside. Once installation is complete, the TBM resumes boring, guided precisely by hydraulic jacks, paving the way for the Evergreen Line, opening fall 2016. The construction of the combined motorway and railway route between Adler and Alpika service stands as one of the most technically demanding infrastructure projects ever undertaken in the region. Achieving this alignment demanded an extraordinary number of tunnels and bridges, resulting in a record-breaking 50 kilometers of installations within just a 32-kilometer section of the SK most contractual area. All structures were built to withstand seismic activity of up to 9 points, which required heavily reinforced concrete and the installation of shock absorbers on bridge supports. Tunneling presented some of the greatest challenges. Engineers had to maintain a stable circular cross-section while cutting through loose rocks of varying density, often under pressure from confined groundwater. Preparatory works such as developing construction platforms and building a network of access roads were nearly as demanding as the main route construction itself. In the first year alone, crews built 11 access bridges and 20 kilometers of new roads, while upgrading 30 kilometers of existing ones. A tunnel lining production facility was established in the Riyadh lowland, which required elevating the entire site due to a high water table. Work along the route demanded an unprecedented concentration of equipment. Up to 30 drilling rigs operated simultaneously to construct bridge piers and retaining walls, while hundreds of cranes, trucks, and earth-moving machines worked continuously. Up to 6 tunnel boring machines were employed, including powerful units with cutting diameters of 10 to 13 meters purchased specifically for the Sochi project. Different tunneling systems used different methods. For example, the first gallery was driven by the Lovat 232 TBM with a 5.9-meter diameter, while adjacent motorway and railway tunnels relied on alpine miner machines and drilling and blasting. The longest tunnel system number 3, over 4 kilometers, used 4 TBMs operating at once, including the 10.2-meter Lovat 394 advancing from the south, combined with conventional mining from the north. Other tunnels used drill and blast or specialized machines, such as the Herrenknecht 10,690 TBM. In unstable soils, jet grouting was widely applied to stabilize tunnel faces and slopes. By 2012, more than 30 kilometers of underground works and 45 bridges totaling 20 kilometers had been completed, marking an exceptional pace unmatched since the construction of the historic Baikal-Amur Railway. The dramatic breakthrough of a tunnel boring machine, TBM, completing its drive for Tunnel A of the East Side Access Project in Long Island City, Queens. On December 26, 2011, the TBM reached its receiving pit, marking the end of a challenging excavation that be. Tunnel A will eventually play a crucial role in the East Side Access System, carrying westbound Long Island Railroad trains into the future Grand Central Terminal concourse. After completing this breakthrough, the TBM will be carefully disassembled inside the pit, lifted out in sections, and transported on flatbed trucks to a new launch point at 29 to 76 Northern Boulevard. There, it will be reassembled and prepared to mine Tunnel D, which will carry eastbound trains departing Grand Central Terminal. When the entire ESA project is finished, 4 parallel tunnels will provide a new, modern rail connection into Manhattan. The Hollandse-Brug, an essential link between Amsterdam and Schiphol, recently underwent a remarkable construction phase involving the installation of 8 precast concrete bridge piers. Each pier weighed up to 64 tons, which required advanced engineering methods, precise planning, and specialized lifting equipment. This operation not only demonstrated technical expertise, but also ensured the long-term stability and durability of the bridge. To begin with, the process started at the fabrication plant, where the massive concrete piers were manufactured with exact dimensions and reinforced with steel to meet design requirements. Once completed, the piers were carefully transported to the construction site. Because of their extraordinary weight, heavy-duty transport vehicles with multi-axle trailers were used. Moreover, logistics planning was critical, since the delivery had to avoid disrupting traffic while ensuring safety along the route. Once the components arrived on site, the next step was to prepare the installation area. Before lifting could commence, the ground and foundation had to be reinforced and checked for load-bearing capacity. In addition, survey teams employed advanced positioning technologies such as total stations and GPS equipment to mark the exact location of each pier. This preparation stage was essential, as even a small deviation could compromise the alignment of the bridge deck. Subsequently, cranes with exceptional lifting capacity were brought in to hoist the piers into place. Each pier was slowly raised and maneuvered with great care, while engineers monitored its movement from multiple angles. Furthermore, temporary supports were positioned to stabilize the structure during placement. Once lowered into its designated position, the pier was adjusted with millimeter precision until verticality and alignment were perfectly achieved. Afterward, the focus shifted to securing the piers permanently. Connections between the piers and the foundation were strengthened with reinforcing bars and additional concrete pouring. At the same time, joints were sealed to create a continuous and durable load-bearing system. During this phase, strict quality control procedures were carried out to test the strength of the concrete, the reliability of reinforcement, and the stability of the entire structure. In the following stage, inspection and verification played a crucial role. Engineers conducted thorough checks to confirm that each pier stood upright within tolerance levels and could withstand both static and dynamic loads. Measurements were compared with design data, while safety tests simulated real conditions. Only after these verifications were the piers officially approved for integration with the bridge deck. Finally, the successful installation of the 8 concrete piers marked an important milestone in the Hollandsbrug project. The combination of heavy lifting technology, precise surveying, and effective teamwork ensured that the operation was completed efficiently and safely. Moreover, the achievement reflected the high level of coordination among designers, builders, crane operators, and supervisors. The pipe installation process begins with preparing proper bedding for both metal and thermoplastic pipes. The bedding consists of PENDOT number 2, a aggregate material which must not be compacted at this stage. Pipes are placed with their bells or grooves facing upgrade, ensuring that the spigot ends are fully inserted into the hubs. If necessary, lift holes are sealed using manufactured lift hole plugs that must remain soil tight. Pipe alignment and grade are controlled using sustainable string lines, an electric laser beam system, or another approved method, while maintaining a minimum slope of 0.35% for all drainage pipes. Next, pipe sections are joined in accordance with Section 601.3N. Joint gaps must be checked continuously, and work must stop if tolerances cannot be maintained, as excessive gaps can lead to long-term infiltration and higher maintenance costs. For concrete pipes, a sufficient layer of caulking is applied to the bell end. Excess caulk is removed after assembly, and the outer circumference is sealed. Elliptical concrete pipes also require 2 layers of Class 1 geotextile wrapping. Metal pipes are joined using 12-inch wide bands. If band dimples do not index properly, the joint is wrapped with geotextile. Thermoplastic pipes use preformed gaskets installed to manufacturer standards. Where pipes connect to end walls or drainage structures, the exposed ends are placed flush and finished with mortar. Backfilling begins along the pipe sides using a coarse aggregate placed in 4-inch compacted lifts with a jumping jack or vibratory plate. Proper lateral support is critical, especially when using shoring or trench boxes. Finally, backfill above the pipe crown is placed without direct compaction 1 foot for metal and thermoplastic pipes, and 2 feet for concrete pipes. A aggregate is required when pipes lie beneath existing roadways, shoulders, or within 4 feet of the subgrade.